a new way to manipulate electrons for the purpose of quantum computing in silicon. So it's my clicker works. It always happens to me. Does it happen to you? There we go. Okay, so I have to start the story by introducing the main characters. So let me start with the people. So up on top, I'm listing all of the members of my group who've contributed to this work. I want to especially highlight my postdoc, Xin Kai, and graduate student Elliot Connors. They've done the lion's share of the work that you'll hear about today. In the middle, this is a picture of the generalized Nichol group. I call it the Nichol group and friends. This was a picture we took this summer. And then we received the semiconductor material we used to do this work from HRL Laboratories. And most of this work was funded by the Army Research Office. So one of the main themes of research in my group at the University of Rochester has to do with quantum computing with electron spins in semiconductors. And there are a variety of different sort of thrusts within this main topic that we are interested in. So one has to do with maybe the nuts and bolts of electron spin qubits. We're interested in making single and 2 qubit gates work as well as possible. We're interested in understanding the different noise properties that affect these things. We're interested when we have chains or systems of a few qubits, things like transmitting information from one side of the chain to another, things like quantum teleportation. We're also interested in simulating the different kinds of things that can happen when one has multiple spins interacting in a chain. We're also interested in hybrid quantum systems. We're interested in exploring how can we, for example, transduce information from the spin degree of freedom to perhaps a superconducting microwave photon, or even some kind of a mechanical system like this. So for my money, as you maybe guess, I like to think that electron spins in semiconductors are really good qubits. And this is really for 2 reasons. One, in some sense, it's the simplest and easy to understand qubit. So probably the electron spin in a magnetic field is the first qubit, the first quantum 2-state system that we all learn about. So an electron has spin 1/2, and it can point either up or down in a magnetic field. So it's a qubit. It's a really easy to understand qubit. Another reason that electron spins in semiconductors are really good qubits, again, this is what I like to think, they have extremely long coherence time. So the coherence time of a single electron in isotopically pure silicon can be longer than 1 second. Maybe it doesn't seem like a long time on regular everyday timescales, but when you think of the typical gigahertz precession frequencies of an electron, indeed, this is a very long time. They're also scalable in the sense that they're very small, typically tens to 100 nanometers or so in size, and they're made out of semiconductors. So it's not inconceivable that one could imagine leveraging all of the advanced semiconductor manufacturing technology at a place like Intel, for example, to create a large 300 millimeter wafer of electron spin qubits. How do we make qubits out of electron spins? So that the technology that we tend to use is something called a quantum dot. You've maybe heard this term before, you know what it means. There are lots of different kinds of quantum dots. Really, a quantum dot is just a confining potential for electrons. It's just a box for electrons. And so there are lots of different kinds of quantum dots. The particular type that we tend to use is called a gate-defined quantum dot. So here are some different pictures of gate-defined quantum dots. I want to draw your attention to this picture down here. Maybe I'll shift to using my pointer. So this one down here. So this is a picture of a gate-defined quantum dot that one might make in a silicon germanium structure. So you can see some metal gates on the surface of this heterostructure, and then in green, there are 3 different layers. So this is a silicon germanium layer. The very narrow green layer here is a thin silicon quantum well. It's typically 5 or so nanometers thick, and then another silicon germanium spacer layer, and then these metal gates on top. So when we apply positive voltages to these gates, because of the band gap mismatch between these different materials, we can accumulate electrons in this quantum well. So actually, here you're seeing a plot of the conduction band edge as a function of vertical position. So you see right here, the conduction band edge dips when you get into the quantum well. And so when you apply positive voltage to these gates, you can accumulate electrons down here. So the different colors here, purple, blue, and yellow, represent different layers of metal gates that we put on top of this structure. And when we dial in the voltages just right, we can create kind of a double well potential here. Really, there can be any number of wells. In this case, it's a double quantum dot. It's a double well potential. And we can confine just 2 electrons here in this structure. So this is how quantum dots work. It's how we physically create electron spin qubits. Yes. Yeah, that's a great question. The role of that is, if we didn't have it, you would be applying positive voltages to sort of this, you would be accumulating electrons in this whole swath of area. So this one is often called a screening gate, and it prevents the electrons from sort of going back. Yep, that's a good question. So there's been a huge amount of progress, actually really over the past 20 years, in quantum dot and spin qubit technology. So the very first quantum dots that were used for spin qubits really looked like this. This kind of a device confines just 1 electron. We use it to make a single spin qubit. Sometimes it's called a Loss-DiVincenzo qubit. Today, now 20 years later, there are systems of 9 single spin qubits interacting with each other. One of the fun things about this field is that there are lots of different ways to make spin qubits. So the simplest is just 1 electron spin, which makes 1 qubit. But you can also make a single qubit out of 2 electrons. This is called a singlet triplet qubit. You can also make 1 qubit out of 3 electrons, and it's called an exchange-only qubit. And again, from early work in the early 2000s to today, there's been a lot of technological advancement, and all of these systems have very high fidelities by now. All right, so let's go back to the case of just 1 electron spin. Let's imagine that we have one electron and it's our qubit. If we'd like to implement any kind of arbitrary quantum operation on this electron, we need the ability to rotate it, if you like, anywhere in space. For any kind of qubit, we need to be able to move the block vector anywhere we'd like on the block sphere. This is exactly what's happening when you think about the expectation value of the spin for an electron. So let's suppose we start with an electron spin up, and we'd like to make it, let's say, spin down. How should I do this? Here's where audience participation is required. What's maybe the best, or what's a good way to do this? Yes? Hit it with a microwave pulse. You're exactly right. In case I needed to give you a hint, I was going to flash the picture of principles of magnetic resonance. Seemed appropriate for Urbana. I don't know if the students have this book. I've actually purchased this book twice, and I've loaned it to students, and it's just, both of my copies are gone, which is too bad, because now it's $150 or $200 on eBay. It's really a shame. But you're exactly right. We should use magnetic resonance to manipulate this spin. So the idea is we apply a large static quantizing magnetic field, and then apply a perpendicular oscillating magnetic field. Those 2 control knobs will let us point the spin anywhere we'd like to in space. So given that lots of spin qubits are in quantum dots, we need to ask, how can we implement this kind of a technique in semiconductor quantum dots? So there are a couple of different ways, more than a couple. There are a few different ways we have to do this. One of them is to do literally just that. We will create a very small, very localized rather, perpendicular oscillating magnetic field. So here's an example of a device where this is actually a donor spin, and then right next to it is this wire, and typically one drives an alternating current through this wire, which then creates an alternating magnetic field. And if you get the geometry right, that's perpendicular to the static field, it drives magnetic resonance. That's one way to do it in quantum dots. Another way to do it is to use a material with strong spin orbit coupling. So this is a case of a semiconductor nanowire. In these kinds of materials, the momentum couples to the spin degree of freedom, kind of like a magnetic field. So if you could imagine that we might create a time-varying momentum, maybe by applying an oscillating electric field and causing the electron to move. That could also drive magnetic resonance. In cases where you aren't working in a material with strong spin orbit coupling, this would be like gallium arsenide or silicon. Another trick you can play is to create a synthetic spin orbit coupling. In this case, it's just a magnetic gradient. So you could imagine if you have an electron sitting in a magnetic gradient, and if you move it back and forth, it will experience an oscillating magnetic field. And if you get the geometry right, that's enough to generate magnetic resonance. All of these techniques tend to work reasonably well, and one generally observes quite nice Rabi oscillations. This is a typical Rabi chevron pattern that you've probably seen before. Right on resonance, there's a series of bright oscillations. Here, the system is going between the two eigenstates, and as you go off to the side, the brightness drops and the frequency increases. So they work well, but you see you need to add typically other stuff to make this work to the quantum dot. So you either need to drive currents close to your device, which can potentially create heating in cryogenic environments. You need to work in a material with strong spin orbit coupling, which might increase your exposure to some sorts of noise, or you need to add this, this extra object that might create a magnetic field gradient. So when we started working on silicon quantum dots, we started seeing things like this in our data. And I'll explain all this to you during the course of the talk, but we saw lots of these characteristic Rabi chevron patterns seemingly popping up out of nowhere, but there are no oscillating fields that we're applying in these experiments. These are purely DC voltage pulses, and yet we're seeing these characteristic resonance patterns emerge. And so that's what I want to tell you about today. These are called coherent spin valley oscillations in silicon. It's a way to manipulate coherently electron spin states without any oscillating electric or magnetic fields. All right, so the first thing I need to tell you about is a little bit about the physics of electrons in double quantum dots. So let's start here. So if I have two electrons in a double quantum dot is just two quantum dots next to each other. If we think about the different possible charge configurations that these electrons can have, we can have one electron in each dot. We might call this the 1-1 charge configuration. Or if we change this parameter epsilon, we'll call it the detuning. If we tilt this double L potential over to the right, both electrons can sit in the right dot. We might call this the 0-2 charge configuration. And if we go the other way, we'll call this the 2-0 charge configuration. This detuning is very easy for us to adjust in practice. It's really just a difference in gate voltage between gates in this double quantum dot. So if we were to draw an energy level diagram of the system, it might look something like this. So in the middle, near epsilon equals 0, the 1-1 charge configuration is the ground state. It has the lowest energy. As we go over to the right, now the 2-0 charge state, 0-2, excuse me, charge state becomes the ground state. And over here, 2-0 is the ground state. The reason that we don't go to 0-2 or 2-0 as soon as we go infinitesimally to one side or the other of 0 is that we have to overcome the Coulomb repulsion. We have to work a little bit hard to put two electrons in the right dot here. Okay. If we decide to allow coherent tunneling of the electrons between these two dots, these sharp crossings turn into avoided crossings. These different charge states are coupled together. So if you look at, for example, this bottom branch, you see now we go smoothly from green to red and back over to blue. Okay, so for most of these experiments, we typically don't have enough energy to go to any of the excited state branches, so let's agree to get rid of them. Now the next thing we have to think about is the exchange statistics of these two electrons in the double dot. So the electrons are fermions. So the overall wave function of these two electrons, which is a product of an orbital wave function and a spinner, needs to be antisymmetric under particle exchange. So there are 4 possible spin states, or let's say basis states of 2 spins. I'm going to choose to write these as the singlet here, up, down, minus, down, up, and the 3 triplets. The T minus, down, down, the T0, up, down, plus, down, up, and the T plus, up, up. Okay? So the singlet spinner is antisymmetric under particle exchange. So if I have two electrons in the singlet configuration, in order for the total wave function to be antisymmetric, the orbital part needs to be symmetric, so that the product of the orbital part and the spinner is antisymmetric. What this means is that the singlet is perfectly happy to occupy any state along this bottom branch here. It's happy to be either in the 2-0, the 1-1, or the 0-2 charge state. That's because both of the electrons can occupy, let's say, the ground state orbital of either the right or the left quantum dot. Okay? They can both sit in the ground state orbital because the spin part of the wave function is antisymmetric. This is not true for the three triplets. They have symmetric spin parts of their wave function, so the orbital part needs to be antisymmetric. That means, in particular, if I have two electrons in one of the triplet states, they cannot both be in the ground state orbital of the same quantum dot. So for sort of moderate values of the detuning here, the three triplets will stay, we say they're polyblockaded in the 1-1 charge configuration. Right? If I want to put two electrons in the same quantum dot in a triplet configuration, I'm going to have to load one into an excited orbital state, which might be a bit higher in energy. This is called a polyspin blockade, and it underlies almost everything that's interesting about electrons and double quantum dots. So for most of the work I'll tell you about, we're going to focus on this region over here. So here's the singlet. Here's the unpolarized triplet, the T0 over here, and the polarized triplet, the T minus. The T minus is split off from the T0 state because we apply a magnetic field. T minus has a non-zero component of spin angular momentum along the z direction. The T0 and S are split by something we call the exchange coupling J, the exchange splitting J. You can think of this as a manifestation, really, of the Pauli exclusion principle. To the degree that the electrons are indistinguishable particles, the singlet will have a lower energy than the T0. The final thing I want to point out here is when the electrons are fully separated over here, when they're in the 1-1 charge configuration, if there are any local differences in magnetic fields between the two dots, for example, there might be a G factor difference between the two dots. The natural eigenstates of the system are no longer the singlet and triplet, but the simple product states, up, down, and down, up. All right, so I have anticipated that there might be some questions here at this point. I really don't want you to have dephased right now before I go forward in the talk. So now is a great time to ask questions if I didn't explain something clearly enough. In fact, I'm gonna, yes.
So you said
Oh, you got it. So if you kept pushing on the detuning this way, maybe right about where I'm standing, then you would see the T0 state turn over into the 2-0 charge configuration. But we're not tilting the potential well enough to overcome the orbital energy spacing of that left quantum dot. We all good? Now's really a good time to ask questions because we're gonna go down the rabbit hole here. Okay. We started to do this in silicon, and all of the slides I just showed you were from some earlier work that I've done in gallium arsenide. In silicon, the situation is a whole lot more complicated. Instead of seeing just states like this, it turns out there are 4 copies, actually, of all of the states in silicon double quantum dots. So here are the T0 and the T minus states that we were looking at before. By the way, I'm going to indicate T minuses with a dash line here. Here's a singlet. There are 4 copies of, well, 3 copies, 4 total pairs of these triplet states. There are actually more singlet states that I'm not showing you here. Why? Why is it like this? It seemed complicated enough already, but now in silicon it's even more complicated. So now I have to tell you about what's called the valley splitting in silicon. So in gallium arsenide quantum dots, if you were to think about, let's say the band structure of gallium arsenide in 3 dimensions, you would see something like this, where the conduction band minimum happens at the gamma point, the center of the first Brillouin zone. And so if you were to imagine drawing a Fermi surface for 3-dimensional electrons in gallium arsenide, you would see just a sphere at the center of the first Brillouin zone. Silicon, however, does not have a conduction band minimum at the center of the first Brillouin zone. It's an indirect gap material. So what this means then is if you were to think about drawing a Fermi surface for electrons in silicon for the kinds of operating conditions in quantum dots, you would actually see 6 equivalent spheroids. This is because of the underlying cubic symmetry of the crystal. So these are the 6 valleys in silicon. There are actually 6 equivalent conduction band valleys in silicon. Now, what happens in quantum dots? Well, when you take silicon and you strain it in a quantum well type of structure, 4 of the valleys are lifted higher in energy by this strain. So then one nominally has two degenerate valleys. These are the, if you like, plus and minus k along the z direction valleys. If you look at the wave functions of the electrons in these 2 valleys, this is what they look like. So here the horizontal direction is actually going up the heterostructure, and this black line is representing the potential. So this dip in the potential is the silicon quantum well. So you see that there are 2 possible wave functions, in a sense, for electrons in this quantum well. Both are oscillating rapidly. You might not expect this on the face of it, but the reason they're oscillating rapidly is that the conduction band minima are near the edge of the first Brillouin zone. And if you look close to this interface here, you can see that the phases of these wave functions are opposite. And so what happens in practice is that these valley states here, which are really properties of 3-dimensional bulk silicon, are actually mixed and coupled by the details of the interface in this quantum well and any electric fields that are applied. They're coupled together, right? These eigenstates here, these are the block wave functions of the full semiconductor crystal. These are not the eigenstates in the quantum well. What the quantum well does is to mix these eigenstates, it couples them, and there's a splitting that results. And that splitting is called the valley splitting. So that's typically something on the order of 10 to 100 micro eV in silicon quantum dots. So instead of thinking that the electrons are occupying, let's say in the ground state orbital, just one state, for a given orbital states, there are actually 2 valley states in every silicon quantum dot. So now I have a minus state and a plus state. Now I have 2 quantum dots. Each quantum dot has a minus state and a plus state. So there are 4 possible copies of the different states in this problem. Yes. Correct. But they are split now by the details of the interface and the electric fields that we apply in the problem. So that's the key point. They're 2 nominally degenerate valleys, but they're mixed by the details of the confinement potential. Jim. That's right.
So what kind of
Yeah, great question. It's this plus e to the I phi that. So there is a phase. It's called the valley phase. It's that, and it's related to whatever details of the interface are going on over here. Yes, yes, absolutely. Fabrication and any electric fields that we apply, absolutely. So the two green ones here are picked by the growth direction of the semiconductor crystal. That's what defines the z-axis in this problem. Right, that's a good question. So at the gamma point, the crystal momentum is 0. Crystal momentum it's kind of like real momentum. And when you go farther away from that, then effectively the electrons pick up more momentum. So they oscillate in space. It's your condensed matter solid state physics in practice. Okay, so in silicon now, in this double quantum dot, now we need to think about minus state and a plus state for each quantum dot. So that's why there are four different sets of triplet states here. One fine point I need to bring into this discussion here, which you can ignore after I finish telling you about it, is that instead of 2 electrons, we are actually using 4 electrons in these experiments. I can tell you why if you're curious after. What you can imagine is because we have 3 of them in one dot, the 2 of them effectively pair up as a singlet and don't really contribute to any of the dynamics I'm going to tell you about. So the lowest energy triplet states are the T minus plus minus and the T0 plus minus. What do I mean by that? Well, so this picture here indicates the spin state up plus down minus. So I have a lone spin up in the plus valley state of dot 1 and a spin down in the minus valley state of dot 2. Okay, actually this picture represents a Slater determinant because the overall wave function needs to be totally antisymmetric, but you get the idea. When I think about something like an S plus minus, which is the state down here, that's just up plus down minus, minus down plus up minus. So the arrows are telling you the spin states in the separate dots, and the superscripts are telling you about the valley configuration, the valley state that each spin is occupying. So we have a T minus plus minus, T0 plus minus. Then the next set of states here involves exciting one of the spins in dot 1. So the yellow states here involve, for example, one of these electrons down here being up here. So the next set of triplet states are lifted by the valley splitting of dot 1. Then we have the plus plus valley states that are lifted by the valley splitting of dot 2. And then finally, the minus plus valley states that are lifted by the sum of the valley splitting in dot 1 and dot 2. Now, after you all thoroughly understand valley physics in silicon, the next important question to ask is, do the valley and spin degrees of freedom of these electrons interact? And this is now where this starts to get interesting. Let's go back to the case where we have just a single spin. If I imagine plotting the energy levels of that single spin as a function of magnetic field, you'll see the Zeeman splitting start to emerge. Okay. Here we have spin down and then spin up. They're split by the Zeeman splitting. Nothing too surprising here. But now if we bring valleys into the picture, this is the diagram that we have to keep in mind. We can have one spin over here. We have one set of energy levels associated with the minus valley state. And then slightly higher in energy, we have another set of levels that do the same thing with a magnetic field associated with the plus valley state. What's interesting is you see that they cross right here at this particular magnetic field. So if there's any coupling between the spin and valley degrees of freedom, you might expect interesting things to happen at exactly this point. I'm going to skip this slide. Indeed, we'll just summarize this briefly. So indeed, this is what spin valley coupling allows to happen. If you include a spin valley mechanism, which arises from spin orbit coupling in this material into the Hamiltonian, that effectively looks like a matrix element in the overall Hamiltonian that, let's say, couples two states that have different spin and valley quantum numbers. So this spin valley coupling can drive a transition from down plus to up minus. This has been seen before in silicon, but typically only in very slow measurements. And it's been seen before only through its effects on spin relaxation in the system. So here's the diagram I showed you before. Here we have the spin states of the minus valley splitting as a function of field, the spin states of the plus valley splitting as a function of field. Here at this avoided crossing, typically one observes a drastic increase in the relaxation rate of the system. The T1, the effective T1 of the spin states really plummets because you have this coupling between these two levels that are very close to each other in energy. Okay. If your control knob for the system is a magnetic field, you can't really do anything fast or coherent with this. It's not possible to change the field of the large solenoid in your fridge on nanosecond timescales. So the advantage that we have in the system is, let's suppose we change the magnetic field now so that this yellow T minus is coming into resonance with these red states over here. Now, if there's spin valley coupling in this system, because of the voltage control we have over the system, now you can imagine doing this very quickly and taking advantage of this coupling to perform coherent spin operations. Okay. So, yeah. Yes, I increased the magnetic field. Yep. That's a slow thing. That's a slow thing. So the difference between the T0 and the T minus is always the Zeeman energy, the static Zeeman energy in the problem. Other questions? Great. That's a great question. Because they have zero component of angular momentum along the z direction. So the singlet state has m equals 0, and the T0 state also has m equals 0. It's only the T minuses that have m equals -1. Yep, great question. So here's the device we use. It's a double dot in silicon. I'm happy to tell you about how we make this a little bit later. We have a charge sensor over here, and we operate this thing with 4 electrons in it, as I mentioned before, 3 in one dot, 1 in another. All of our experiments will start by initializing this S plus minus state. That's the lowest energy state in the system. We'll then manipulate the system and then project back out along that direction. Okay, so let's do the experiment that we just talked about earlier. So let's increase our magnetic field to 279.2 millitesla. So when we do that, that brings all of the spin polarized levels down. So the Zeeman splitting went from this small arrow here now to this large arrow here. Now you see that this yellow dashed line is intersecting the red line here. So we might expect interesting spin valley physics to happen there. So let's zoom in right here. Okay, here's what the energy levels look like. One thing to keep in mind here is that over here, when the electrons are fully separated, the natural eigenstates of the electrons are up, down, and down, up. So the relevant eigenstates to think about here are down, up, and up, down. We're working in the plus minus. We initialize as a plus minus singlet. So that plus minus singlet will go to the down plus up minus. Then we have this T minus 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 cutting through. So that's a down down minus minus cutting through. So now you can ask yourself, if there's spin valley coupling in the problem, what should happen? Well, Look at this down plus up minus state. There's not a good way for that to transition to the down minus state, right? What would have to happen? Well, this first spin would have to just change its valley configuration. It would have to go from plus to minus without changing its spin. That process is slow. This one would have to go from up minus to down minus. It would just have to relax without changing its valley configuration. That process is also slow. If we start with the up plus down minus state, now you can see that that's just one spin valley flip away from the down minus state. All we need for that to happen is for the left spin to go from up plus to down minus. And that's exactly the sort of thing that spin valley coupling allows to happen. So if we prepare the down plus up minus state, and if we pulse to different values of this detuning, don't see much happening, right? That's what we might expect. If we prepare the up plus down minus state and pulse to different values of the detuning, now we see these Rabi oscillations start to appear. So these are transitions between up plus down minus to down minus. And this happens with a frequency of 8.2 megahertz. Okay. Let's change our field to 380.8 millitesla. Why not? This purple state is going to come into resonance with the red state over here. Now we have a larger Zeeman energy. Now, if you zoom in and look at this energy diagram, we still have these familiar states, up plus down minus and down plus up minus. But now the state that's cutting through is an up plus state. So you can see that there really isn't a good way to go from, down plus. This is even trickier. This is even tricky for me here. There really isn't a good way to go from the down plus state to the up plus down minus state. The left spin would have to just spontaneously flip, and the right electron would have to change its valley state without changing the spin orientation. You can see though that down plus is just one spin valley flip away from down plus up minus. Here, the right electron that changes both its spin and valley quantum number at the same time can make this transition. That's what spin valley coupling allows. So now if we prepare the down plus up minus state, that's this one here, and we pulse to different values of the detuning, now we see these clear Rabi oscillations start to come through. Remember, this was the case last time where we didn't see anything. The reason we're seeing something now is that we have a different triplet state. And if we prepare the up plus down minus state, now we don't see anything before. Okay, what's going on? Well, let's look at the case that we were just looking at. Transitions between down plus up minus and down plus. So here's the down plus state. So in each dot, there are two valley states, a minus and a plus. This is how you should think about the down plus state. So here's the electron in dot 1, it's spin down in the plus valley state, the electron spin down in the plus valley state in dot 2. Here's the down plus up minus state. Everything is the same except the electron in dot 2 is spin up, but in the minus valley state. So these Rabi oscillations then that we just saw, these correspond to transitions between these two states. Is literally the electron in dot 2 that's going from up to down, and at the same time it's going from minus to plus. So these are coherent spin valley oscillations in dot 2 here. Here's a picture that shows you that the transition between up plus down minus and down plus, that can't happen very easily. Again, because we would need the electron in dot 2 to simultaneously change its valley state and also change just the spin state over here in dot 1. Yeah. So that's a great question, and my my answer to this is within like a very simple Slater determinant picture where you create the full 4 electron wave functions out of these single particle states. You know, there's no effect of those two sitting down there. They're just a singlet. It's certainly a very interesting question that I don't have a good answer to. You know, are there many body effects that oh. Right. Yeah, you absolutely could. So the advantage though of doing this with, let's say 2 or 4 electrons is that you can use all of the electrical control that kind of the singlet triplet platform allows you to do. So something I haven't talked about at all is with singlet triplet qubits as opposed to single spin qubits, the control is almost entirely electrical and it's much faster than for single spin qubits. But in principle, yes. Any other questions? So that's another great question. It's one that I don't have a satisfying answer to. What we know is that if the interfaces in the semiconductor structure were perfect, the spin valley coupling would be 0. So in some sense, this does rely on defects. You know, they could be atomic steps or something like that in the system. And so that's actually a really interesting question that's worthy, I think, of a lot of future work. Right. Right. Yes.
So that, but you see the same ladder here.
Yes, typically, and we have seen this same overall structure in multiple different devices, but exactly where that happens and exactly the frequencies depend on a lot of details that we don't have a good handle on. Yeah. Absolutely, it's tunable. Okay. For my next trick, let's go to 295.0 millitesla. Why not? Now you see this yellow line. One of the minus states is cutting across the plus minus states down here. So let's zoom in here. The relevant eigenstates of the plus minus manifold are kind of the regular singlets and triplets that I introduced to you before. Here, the exchange coupling is appreciable. So this is what spin valley coupling does. This is the matrix element that spin valley coupling creates. It's a connection between, let's say, up minus and down plus. We no longer have product states here. Here we need to think about singlets and triplets. So let's ask the question, what is the matrix element of the Hamiltonian between S plus minus and T minus minus here? These are the relevant states now. It looks a little formidable, but all we need to do is just expand out this singlet, which is up plus, down minus, minus, down plus, up minus. And so this matrix element here really is the sum of 2 matrix elements. So the first is the matrix element between up plus, down minus, and down minus, down minus. And then the second is the matrix element between down plus, up minus, and down minus, down minus. See how I got that? I just wrote out the singlet state and separated out this matrix element. Okay. This one is 0. There's typically not really a good mechanism in the Hamiltonian that can just flip a spin without changing the valley configuration. So the electron in dot 2 would have to go from up to down. The electron in dot 1 would have to go from minus to plus. Again, there isn't really a good way for this to happen. If you look over here, though, the electron in dot 2 doesn't need to change. The electron in dot 1 needs to undergo a spin valley flip. Okay, but the key difference here is this factor of 1 over root 2. So the matrix element between the S plus minus and the T minus 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 is the same as this single spin matrix element, except multiplied by a factor of 1/√2. Okay, so now you know where I'm going with this. Here's what we saw in the experiment. Now, instead of preparing this product state, we prepared the singlet state. We still see these Rabi oscillations occur. Now it's at a frequency of 6 megahertz instead of 8 megahertz, which is pretty close to 1/√2 times 8 megahertz. We can nicely predict what it is that we should see. My last trick, let's go to 372.3 millitesla. Let's zoom in here. This purple line cuts across the plus minus curve twice. That's kind of interesting. So we should see 2 avoided crossings here. Again, because the relevant states are singlets and triplets here as opposed to product states, we should see this factor of 1/√2. Indeed, we see these 2 sets of chevrons that emerge, again, with a frequency that's 1/√2 times what we saw in the single spin case. Okay. If you stare at this, and if you ask yourself what would happen if we decrease the magnetic field just a little bit, here this green line is cutting through the plus minus branch twice. If we lower the field just a little bit, that green line will shift up, and we should see kind of a nice, really extended sort of flat top region of these Rabi oscillations. Again, we see that with the same frequency. It's 1/√2 times what we got for the single spin case. All right. If you think about it now this is in a sense a new qubit that we have to think about. The single spin valley qubit was also kind of a new qubit in the sense that it's a new way to manipulate single spin states. Now you can think about making singlet triplet T minus qubits. It turns out to work pretty well. We can do Ramsey experiments where we measure the precession frequency and the dephasing time of the system. We can do a spin echo, which increases the coherence time from a few hundred nanoseconds to more than a factor of 10 larger. One thing I do want to point out is this unusual feature right here. So this is the same configuration with this large sort of flat sweet spot that I mentioned earlier. If you stare at this unusual stripe here, you can convince yourself that this is actually an interaction between the T minus and the T0 states. That should happen as a result of spin valley coupling for exactly the same reason that the singlet to T minus coupling happens. And so if we do an experiment where we do a pi pulse on the singlet to T minus transition to prepare T minus, and then if we change the detuning over here, now we can see these coherent. Computer is no longer coherent. We can see these coherent T0, T minus transitions coming in here. That's these. They have the same frequency up to a phase shift as these, as they should. Okay. All right. Let me skip over this and just tell you about where we might think about going next. So there were a couple questions about fundamentally what is it that causes this spin valley coupling, and we know it has to do with interface roughness in the system, but I think the broader question of how can it be manipulated or tuned, and how does it depend on the various parameters we have at our disposal is a really interesting question. We have this family of new spin valley qubits, single spin, singlet, T minus, T0, T minus qubits. How well do they work? What are their gate fidelities? What are the limiting factors? I think also thinking about 2 qubit gates between these systems is also a very interesting question. So let me now just wrap up and remind you that we've talked about electrons as qubits. We talked about quantum dots. We've talked about valley splitting in silicon. We've talked about how these things kind of come together in the form of spin valley coupling in silicon quantum dots. And I've shown you coherent spin valley oscillations in silicon, which is really a new way to manipulate electrons using only DC, only baseband voltage pulses. No high frequency fields required. And if you're curious to read more about this, you can check out our recent paper. So thanks for your time, and I'm happy to take any further questions. It's a great question. So a good way is potentially through exchange coupling. So if you imagine two qubits here, the middle two qubits, if their wave functions overlap, can interact via exchange coupling. There are a lot of interesting and complicated questions there, like you might imagine. So it turns out that this actually works really well for kind of regular singlet, triplet T0 qubits. We think it works also well, but differently for the case of these like T- qubits. That's a really good and really loaded question. What I will say is what's the best way to say this? So there's a substantial contribution to the energy splitting of this qubit from electric fields. It depends on electric fields. And so one of the main sources of noise here is actually electric fluctuations in the quantum dots. This kind of improvement is actually pretty good for qubits with an energy splitting that depends on electric fields. And that's in part because this dispersion over here is mostly linear and not something like exponential. If I fully knew the answer to that question, I would have a company with all of the funding in the world, and we'd be making the best qubits ever. It's a good one. This is not isotopically purified material. So what Elizabeth is alluding to is one of the main advantages to make quantum dots out of silicon instead of something like gallium arsenide is that you can, in principle, isotopically purify the silicon to remove all of the spinful nuclear isotopes. So there's, in natural silicon, 5% abundance, give or take, of spinful nuclear isotopes. And those are all present in the quantum dots we're using. Other folks do experiments with isotopically purified material, which we do not. Yeah. So as I said, I think the coherence time is mostly limited by electrical fluctuations here. So that's a good question that I do not have a good answer to, but it's an interesting one to think about. No, the spacer layers matter. The germanium nuclear spins, the germanium, any nuclear isotopes that have spin of germanium also matter.
Yeah.
I believe it is. Yeah, and then what? So it's mostly the silicon quantum well for sure. It's mostly the silicon quantum well for sure. Mostly we want that to be isotopically pure, but you see that the wave function leaks out a little bit into the silicon germanium barrier. And if you've removed all of the nuclear spins from here, you will for sure start to feel the nuclear spins in the spacer. They are grown through CVD. I don't know about the substrate. What I can also add is that there's a lot of strain management that happens in these heterostructures too. I don't know if Thaddeus Ladd or Matt Reed want to chime in here. I don't know if Thaddeus Ladd or Matt Reed at HRL who are, oh, Thaddeus Ladd wants to chime in.
Hey, well, we're both online, but we can't hear the questions.
Can you hear me? You can hear me. So the question is,
I can hear you, but I can't hear anybody in the room.
are the CVD substrates grown with a vicinality, with a tilt?
Sorry, what? Are the substrates grown something about a tilt?
Are the substrates tilted when you grow the stack on top of them? Is the substrate cut?
Yeah, there's always a small miscut. Small though. I'm not sure I can quantify that. Can you hear me?
Yes, we can. Thank you for that answer. Sorry.
It also looked like sort of strength of the transition.
See if I can go forward. So is the suggestion that the transition amplitude is a little bit weaker than this case, or? Yeah, that's an interesting question. That's not something we've looked in detail at.